Welcome back to the Deep Dive. I'm Adam.
And I'm Grace.
We're both grade 8 science teachers here at School on X, and we are absolutely thrilled to have you, our incredible grade 8 learners.
Yeah, and anyone else out there, too.
And frankly, anyone else out there with a burning curiosity, join us for another deep dive into the fascinating world around us.
That's right. Here on the Deep Dive, our mission really is to take what might seem like complex scientific topics, unpack them with, enthusiasm,
Absolutely.
and reveal those essential, maybe surprising insights that make you truly well-informed. We sort of aim to give you a shortcut to understanding the bigger picture.
Yeah, helping you connect the dots between what you learn in class and, well, what you observe every single day.
Exactly.
And today, we're going to ignite your understanding of a fundamental process, one that touches almost every part of our daily lives. Just think about it for a moment. Lighting a candle for a birthday celebration, maybe starting a cozy campfire under the stars, or, simply turning on the gas stove in your kitchen to make breakfast.
Right, everyday things.
There's this incredible transformation happening right there, isn't there? It seems like a simple act, but what exactly is that transformation? What's the science behind the sizzle and the flame?
Well, today, that magic gets a scientific spotlight. We're dedicating this deep dive specifically to Chapter 4, Combustion and Flame. That's right, from your grade 8 science curriculum.
Perfect.
We're going to explore this crucial chapter in detail, breaking down the core concepts, diving into the fascinating mechanisms, and making sure you walk away not just like remembering definitions, but truly understanding this fiery fundamental process and its enormous impact on our world.
Okay, sounds like a plan. So let's get started. We're going to begin by really understanding the fiery fundamentals. What is combustion, anyway?
It's a great place to start, isn't it? Because, while we use the word burning all the time,
Yeah, constantly.
the scientific precision behind it is what truly unlocks understanding. It's more than just things getting hot.
Exactly. Think about all the common things we see burning every day or that we use as fuels. At home, maybe it's LPG for cooking or perhaps kerosene for lamps in some places.
Sure.
In industries, well, they might use massive amounts of coal or diesel to power machinery. Huge scale.
Right.
And for transport, we rely heavily on petrol and compressed natural gas or CNG.
Yeah.
And these are all so common, so familiar, but when we say they burn, what's really happening on a fundamental level?
What's truly fascinating here is how intuitively we understand the concept of burning. We see the light, we feel the heat, but often we haven't really stopped to grasp its precise scientific core. Like, consider the difference between a candle, which burns with a distinct visible flame.
Yeah, that flickering yellow flame.
And then think about a piece of coal. It often just glows steadily, maybe red, without a proper flame.
Oh, yeah, good point. Like embers.
Exactly. This simple, everyday observation isn't just a minor detail. It actually hints at the diverse manifestations and underlying complexities of combustion that we're about to explore. It's definitely not a single, uniform process at all.
That's such a great point. It's those small observations that lead to big scientific questions, isn't it? So let's get to the core definition then, the bedrock of our understanding. At its heart, combustion is a chemical process.
Okay, a chemical process.
Right. This means it's a reaction where a substance rapidly combines with oxygen, typically just from the air around us, to produce heat. And often, though not always, light comes along for the ride.
Right, light as well.
Yeah, either as a vibrant flame or maybe just a steady glow. It's not just disappearing, it's transforming into something new, releasing a burst of energy in the process.
And this substance that undergoes combustion, the one that's actually reacting with oxygen, that's precisely what we call a fuel.
Fuel, got it.
And it's vital to remember that fuels aren't just solid materials like, wood or coal, which are probably the first things that pop into your head.
Yeah, usually.
They can also be liquids like the petrol or kerosene you mentioned earlier, or even gases such as CNG or the natural gas piped into homes.
Okay, so solid, liquid, or gas.
Exactly. The key is their ability to react with oxygen and release that energy. The light, as you said, can manifest as that dancing, flickering flame we associate with, like a bonfire, or maybe a more subtle, consistent glow, like the embers of charcoal after the main flames have died down.
We've actually seen this exact chemical dance in action before, even back in our Class 7 experiments. Remember that?
Oh, yeah, magnesium ribbon.
Yes. We took that magnesium ribbon and watched it burn with such a bright, almost dazzling white light.
So intense.
It transformed into magnesium oxide, and it gave off both intense heat and that brilliant light. It was a classic example right there of this chemical process playing out, a little miniature combustion reaction.
And similarly, if you think about charcoal, something maybe more common, when charcoal burns in the air, it produces carbon dioxide along with heat and light. These examples, from the very reactive magnesium to the common charcoal, they beautifully illustrate that the fundamental elements are always at play.
What are those again?
A substance reacting with oxygen to produce heat and often light. The specific fuel changes, maybe the speed changes, but the core chemical principles stay the same.
Okay. Now, here's where it gets really interesting and maybe a little surprising for some of you listening. You've probably heard people say that food is fuel for our bodies.
Right. Yeah. All the time. Fuel up before a game, that kind of thing.
Exactly. When you first hear that, it might sound like just a catchy, metaphorical phrase, doesn't it?
Yeah.
But is there a genuine scientific basis behind that idea? Or is it just a clever way of speaking? Because, on the surface, it sounds quite different from a roaring fire.
It's absolutely not just a catchy phrase.
Yeah.
And this is one of those insights that really makes you pause and think.
Okay.
Indeed, just like wood or coal, the food we consume is broken down inside our bodies. It happens through a complex series of reactions with oxygen that we inhale.
So oxygen is involved there too?
Definitely. And what's the result? Well, heat is produced, among other things, which helps keep our body temperature stable.
Okay.
This process, which we actually touched upon back in class 7 when we discussed respiration.
Right, respiration.
It is a form of combustion. But, and this is key, it's a uniquely sophisticated and highly controlled one.
Controlled, so not like a bonfire inside us.
Exactly. Our bodies don't just burst into flames, thankfully. Instead, they meticulously orchestrate millions of tiny, controlled chemical reactions.
Millions. Wow.
Yes, slowly and efficiently capturing that energy release. Unlike an uncontrolled bonfire where, most of the heat just radiates away, our bodies precisely manage this internal burning to maintain body temperature and generate the energy in the form of ATP molecules that fuels our every activity.
ATP, the energy currency.
That's the one. From thinking to running, it all needs that energy. It highlights that the fundamental principles of combustion aren't just for dramatic flames or industrial processes. They're integral to the very essence of life itself.
Wow.
It's like an amazing engineering marvel built right into our biology.
That's truly mind-blowing when you think about it that way. The same fundamental process powering a car engine is, in a very different controlled form, powering us.
Precisely.
So thinking like scientists now, just as we do in the lab at School on X, we can actually categorize materials based on whether they undergo combustion or not. This is a very practical scientific skill.
It is. Classification is key.
Okay, so let's try a mental exercise. Everyone listening, grab a mental list of these materials.
Yeah.
Straw, matchsticks, kerosene oil, paper, iron nails, stone pieces, and glass. All right. Based on what we just discussed, which ones do you think are combustible? And which ones are non-combustible? Just think about what happens if you tried to light them.
The key, as you've perfectly outlined, is simply observing if combustion takes place under, let's say, normal conditions.
Right.
This seemingly simple act of categorization, much like Activity 4.1 in your textbook, helps us understand the intrinsic chemical properties of different substances.
So which ones burn?
Well, paper, straw, matchsticks, and kerosene oil, they readily burn under appropriate conditions, indicating they are combustible.
Okay, makes sense.
But things like iron nails, stone pieces, and glass, typically they do not burn, making them non-combustible, at least not easily.
Right. So this initial observation then naturally leads us to a more critical question.
Right.
What are the specific indispensable conditions that are required for anything to actually burn? Because it's clearly not just about the material itself, is it?
Exactly. It's not enough just to be combustible.
Precisely. That brings us to the next crucial part of our deep dive. You might think, you just need a spark to get a fire going, and boom, you have a flame.
Yeah, seems simple.
But it's far more nuanced than that. We need to understand the fundamental conditions for combustion.
Okay.
Let's explore this with a classic experiment. Imagine using a candle, a glass chimney, and some wooden blocks. It's much like the setup you see in Figure 4.2 in your textbook. It's a brilliant way to demonstrate the role of air.
What's so insightful about this controlled experiment and why we do it in class is how clearly it demonstrates the indispensable role of air, or more specifically, the oxygen within the air.
Okay, show us how.
Right. So in the first scenario, picture the candle inside the glass chimney, and the chimney is raised up slightly by wooden blocks underneath it.
So air can get in underneath.
Exactly. Air can freely enter from below, and what happens? The candle burns brightly and steadily. No problem. Then, scenario 2. You remove the wooden blocks. The chimney rests directly on the table. Now, the air supply from the bottom is significantly reduced, almost cut off.
What happens then?
Well, the flame flickers, it becomes unstable, and you might even see it producing some smoke.
Smoke. Why?
That smoke is a sign of incomplete combustion. It's happening because there isn't enough oxygen getting to the flame anymore.
Ah, okay. Incomplete combustion.
And finally, scenario 3. You cover the chimney completely with a glass plate on top. Now you've cut off all air supply, top and bottom.
And the flame?
It quickly extinguishes, goes right out. This entire sequence clearly and powerfully demonstrates that air, or more accurately, the oxygen within the air, is absolutely and fundamental necessary for combustion to occur and be sustained.
No oxygen, no fire.
Simple as that. Without it, there's no fire.
So extending that vital idea, think about what happens if you try to put a glass jar over a burning piece of charcoal, like in Activity 4.3. What happens to the charcoal?
Well, following the same logic,
Yeah,
it stops burning, right?
exactly. And consider a real-life situation, something incredibly important for safety. Why do firefighters, or even just ordinary people, instinctively cover someone whose clothes have caught fire with a thick blanket? You see this in Figure 4.3. What's the common thread here?
This raises an important point, and the common thread is beautifully clear. In both cases, the charcoal under a jar and a person covered with a blanket, the primary goal is to cut off the supply of air.
Okay.
Therefore, cutting off the oxygen to the burning material, the blanket effectively smothers the fire. It creates a barrier that prevents oxygen from reaching the burning clothes.
Smothering, I like that word for it.
And without that continuous supply of oxygen, the combustion reaction just cannot sustain itself and the fire dies out. This is a fundamental principle of fire control.
Remove the oxygen.
You extinguish the fire. It's why fire blankets are so effective, say, in kitchens for small pan fire.
Okay, got it. Now let's talk about something else essential. Does a matchstick, just burst into flames on its own, sitting quietly in a box?
No, definitely not. That would be dangerous.
Right. You have to strike it,
Yeah.
create some friction, generate some heat. Why? This brings us to another absolutely crucial concept in combustion. The ignition temperature.
Ignition temperature. Okay.
It's super important to understand not just what it is, but why it matters so much.
Absolutely. The ignition temperature is defined technically as the lowest temperature at which a combustible substance can catch fire and then, crucially, sustain the combustion process.
Lowest temperature. Oh,
It's a critical threshold. If a substance isn't heated enough to reach this specific temperature, it simply won't burn. It doesn't matter how much oxygen is present around it.
so even with plenty of air, if it's not hot enough, nothing.
Nothing. This is precisely why a piece of wood doesn't spontaneously combust at room temperature, even though it's surrounded by oxygen.
Right, thankfully.
However, kerosene oil, for example, might catch fire more easily if it gets just a little warmer than room temperature.
Huh.
This implies correctly that kerosene's ignition temperature is significantly lower than that of wood.
Lower ignition temperature means easier to light.
Exactly. It's all about how much energy those molecules need to absorb to really get going and start reacting properly with oxygen. Some substances are simply, well, more eager to react.
That's a really crucial point about these specific temperatures. So what does this essential understanding of ignition temperature mean for how we handle things? How we store various fuels, especially something like kerosene oil, both at home and maybe in larger storage facilities?
It means we need to take very special care, and that understanding this principle directly impacts our safety protocols. It's not just abstract science.
Right. Practical stuff.
Because kerosene oil has a comparatively lower ignition temperature than many other common fuels like wood or coal, it is considerably more prone to accidentally catching fire.
More risk.
Definitely. Even a small increase in the ambient temperature, the temperature around it, or just a minor spark nearby could potentially be enough to ignite it.
Wow.
This directly relates to vital fire safety measures. Things like proper ventilation, storing these fuels away from any heat sources, ensuring containers are properly sealed.
All makes sense.
It's all about respecting those ignition points and minimizing the risk of the fuel ever reaching that critical temperature.
Let's take a quick, fascinating detour into history now, because science often has a great story behind it.
Always does.
Did you know that the earliest forms of matchsticks, in some shape or form, have actually been around for over 5,000 years. Imagine that.
5,000 years. Wow.
Yeah. The ancient Egyptians, for example, used humble pine wood dipped in sulfur. They were essentially very basic fire starters.
It's true. But the modern safety match, the kind we know and use every day, is actually a relatively recent invention. Only about 2 centuries old.
Only 200 years. Seems like they've been around forever.
Relatively speaking.
Yeah.
And the initial attempts at creating these portable matches used highly volatile and incredibly dangerous white phosphorus.
White phosphorus.
Yes.
Sounds bad.
It was. This substance had an extremely low ignition temperature. That means it could ignite with very little friction or heat. Very unstable. This made it incredibly dangerous, not only for the poor factory workers who were manufacturing the matches that caused severe health issues like phossy jaw, but also for the people using them, as they could sometimes spontaneously ignite just from being carried around.
Oh my goodness.
It was a serious public health hazard back then.
Thankfully, science, driven by that need for safety, intervened and found a much, much safer way.
Good old science.
Today's safety matches, the ones you use every day, use significantly safer ingredients. The match head itself contains a mixture of antimony trisulfide and potassium chlorate.
Okay, safer chemicals.
And the special rubbing surface on the side of the matchbox, that rough strip, that has powdered glass for friction mixed with a tiny amount of red phosphorus. And importantly, red phosphorus is far less dangerous and much more stable than white phosphorus.
Okay, so red phosphorus on the box, not the match head.
Exactly. So when you strike a modern safety match against the box, the friction generates just enough heat.
Right, back to heat.
This heat causes a tiny, almost imperceptible amount of the red phosphorus on the box to convert into white phosphorus. Just a tiny bit right there.
Ah, so it does make white phosphorus, but only briefly.
Exactly. This newly formed white phosphorus immediately reacts with the potassium chlorate in the match head. That reaction generates a small but intense burst of heat.
Okay.
That generated heat is then precisely sufficient to ignite the main fuel, the antimony trisulfide, starting the rapid combustion process we see as a steady, controlled flame.
Wow, that's intricate.
It's a remarkable marvel of controlled, intricate chemical reactions, all orchestrated in a fraction of a second right there in your hand. It truly makes you appreciate the engineering behind such a simple, everyday object.
It really does. Okay, this next activity is truly mind-blowing and one we've actually done in class together. It's the paper cup experiment, activity 4.4.
Ah, yes, always a favorite.
Here's how it goes for everyone listening. Take 2 identical paper cups. Pour about, say, 50 milliliters of water into one cup and leave the other one completely empty.
Okay, one empty, one with water. Now, very carefully, you heat both cups separately with a candle flame. Hold them just above the tip of the flame, the empty cup.
Ooh.
It burns almost immediately, often with a quick flare-up. Paper burns easily.
Of course.
But the cup with water, get this, it doesn't burn at all, even though it's made of paper. And the water inside actually gets hot. You can even boil water in a paper cup using this method, which just seems to defy logic.
It does seem impossible at first glance, doesn't it? Can you think of an explanation for this seemingly impossible phenomenon? It's all connected to what we've been discussing.
It must be the ignition temperature again, right? And maybe how the heat moves.
Exactly. It's all about that critical concept of ignition temperature and how heat is transferred. The heat from the candle flame is continuously transferred directly to the water inside the cup.
Through the paper.
Yes, through the paper, via a process called conduction. The water, in turn, continuously absorbs this heat. It acts as what we call a heat sink.
A heat sink, like it draws the heat away.
Precisely. It effectively draws the heat away from the paper itself. This constant absorption of heat by the water prevents the paper from reaching its ignition temperature.
So the paper just never gets hot enough to burn.
Correct. Even though paper is a highly combustible material, it won't burn as long as the water is there to dissipate the heat away from it and keep the paper below that critical ignition point.
That is so cool.
It's a powerful demonstration of how heat transfer works and its critical importance in preventing combustion sometimes.
That's a fantastic example, and it really drives home the point about needing that specific heat threshold. This leads us naturally to a special category of substances. These are things that have very low ignition temperatures.
Very low.
Because of this, they can catch fire extremely easily, often producing a visible active flame. We give them specific name. Inflammable substances. You need to be extra careful around these.
Yes, the term inflammable can sometimes be confusing because in often means not.
Right, like inactive.
Okay. But here, inflammable actually means very flammable. It's a bit of an oddity in English.
Good point. So inflammable means easily catches fire.
Exactly. Examples are plentiful and absolutely essential to know for safety. Think about petrol, alcohol, liquefied petroleum gas, or LPG, the gas used in many kitchen stoves.
Okay, common fuels.
These substances require minimal heat to ignite, making them a significant and constant fire risk. This is precisely why you see prominent warning signs at petrol stations.
Like no smoking.
Exactly. Or why specific precautions are taken in factories and homes where these substances are stored or used. Understanding this category helps us practice better safety, both individually and as a community, by treating these materials with the caution they demand.
Absolutely crucial. Okay, and that brings us to the next vital segment of our deep dive. We've explored what combustion is, what it needs to get started.
Fuel, air, heat.
Right. Now, let's talk about something equally important, perhaps even more so in terms of safety in everyday life. Taming the flames. How do we control fire?
Putting fires out. Essential skill.
So, you remember we've identified the 3 absolutely essential ingredients for fire to exist. Can you name them again?
Let's see. Fuel.
Yep.
Air, specifically the oxygen in the air.
Got it.
And heat. Enough heat to reach the ignition temperature of the fuel.
Perfect. These 3 elements are often called the fire triangle. If you don't have all 3 of these in place, you simply don't have a fire.
That's the critical understanding, and it's actually good news because the fundamental principle of fire control stems directly from this fire triangle.
How so?
If you can remove or interrupt even one of these 3 requirements, take away the fuel, cut off the oxygen, or cool down the heat, you can effectively control or extinguish a fire.
Just need to break one side of the triangle.
Exactly. This fundamental principle is the entire job of a fire extinguisher, whether it's a simple bucket of water or a complex chemical system. Their design and function are always geared towards doing one or more of those things: cutting off air, bringing down temperature, removing fuel, or ideally, doing a combination simultaneously. It's the cornerstone of all fire safety and firefighting strategies.
So let's talk about the most common fire extinguisher we see. Water. It's our universal hero, isn't it?
Pretty much.
We've all seen firefighters pouring immense amounts of water on a blaze, like in Figure 4.6 in your textbook. But beyond just making it wet, how exactly does water work to put out a fire? What's the science behind its effectiveness?
Water is indeed a remarkable and versatile fire extinguisher. It works in 2 primary and very effective ways.
Okay, 2 ways. What's the first?
First, when water is applied to a burning material, it rapidly cools the combustible substance. It absorbs a lot of heat.
Cooling it down.
Right. This action brings its temperature down swiftly, pulling it below its ignition point. By lowering the temperature, water essentially stops the fire from spreading to adjacent materials and prevents new areas from catching fire.
Okay, cooling is one. What's the second way?
The second way is linked to the heat absorption. The water, when it hits the intense heat of the fire, quickly turns into steam or water vapor.
Right, it boils.
And water expands enormously when it turns to steam. This steam acts like a protective, non-combustible blanket.
A steam blanket.
Yeah. This blanket surrounds the burning material, effectively displacing the air and cutting off the vital oxygen supply that the fire needs to continue.
Ah, so it tackles 2 sides of the triangle.
Exactly. Water offers a very effective 1-2 punch against many fires. It cools the fuel and smothers the flames by cutting off oxygen.
Hardy, here's the crucial moment we hinted at. As effective as water is, it isn't always the answer for every type of fire, is it?
No, definitely not.
For example, can water be safely or effectively used on electrical fires? What about fires involving oil and petrol? It seems like it might be dangerous or just, well, not work at all.
This is an incredibly important safety point, and the answer is a definite and resounding no for both of those scenarios. Do not use water on electrical or oil fires.
Why not electrical?
Using water on an electrical fire is profoundly dangerous because, as you know, water conducts electricity.
Right.
If you were to spray water onto live electrical equipment that's on fire, you would create a significant electrocution hazard. It could harm those trying to douse the fire and cause even more damage. Incredibly risky.
Okay, definitely no water on electrical fires. What about oil or petrol?
Well, for fires involving oil or petrol, water is actually denser or heavier than oil.
Heavier.
Yes. So if you pour water onto an oil or petrol fire, the water will simply sink underneath the burning liquid.
It goes under the fire.
Yes. leaving the oil to continue burning happily on top, floating on the water you just added. It's completely ineffective.
Wow.
And worse, the force of the water can actually splash the burning oil around, spreading the fire and making the situation much worse.
So it makes it worse. Okay.
It's like trying to put out a campfire by pouring water on the ground next to it instead of on the actual flames. It simply won't work because you're not addressing the burning substance itself correctly.
So for those tricky types of fires involving electrical equipment, or those highly inflammable materials like petrol, we need a different hero.
We do.
And that hero is often carbon dioxide, or CO2. This is what you frequently see in those distinctive red cylinders mounted on walls in hallways or labs, like in Figure 4.7. Why is CO2 the go-to solution here?
CO2 is an excellent choice for these specific types of fires, precisely because of its unique properties. Firstly, and very importantly, carbon dioxide gas is significantly heavier than oxygen.
Heavier than oxygen. Okay.
So when it's released from a fire extinguisher, it literally blankets the fire. It flows down and creates a dense layer over the burning material.
Like the steam blanket, but with CO2.
Exactly. It effectively cuts off the oxygen supply to the burning material. This smothering action immediately suffocates the flame. Secondly, and very importantly for electrical fires, CO2 is a non-conductor of electricity.
Ah, that's key.
Yes, meaning it won't create an electrocution hazard, which is a major advantage over water in those scenarios. Plus, it's considered a clean agent for sensitive electrical equipment because it leaves no residue behind.
Okay, non-conductive and no mess. Good advantages. And there's an added bonus to using CO2, isn't there? It's not just about smothering the flame. There's a cooling effect involved too, right? Seems like another 1-2 punch.
Yes, absolutely. That's the second powerful mechanism. CO2 is stored under very high pressure inside those cylinders, usually as a liquid.
Liquid CO2.
Yes, under high pressure. When it's released into the open air, where the pressure is much lower, it undergoes a massive and rapid expansion in volume as it converts from a liquid back into a gas.
Okay.
This rapid expansion process, a bit like how an aerosol can feels cold when you spray it, causes the CO2 to cool down significantly, sometimes to extremely cold temperatures, often producing a visible cloud of tiny, dry ice particles.
Wow. Dry ice.
This sudden, intense cooling effect further helps to bring down the fuel's temperature, pulling it below its ignition point, making it even harder for the fire to restart. So you have both the smothering effect from displacing oxygen and the cooling effect working in tandem.
Double action. Very effective.
Very. And an interesting side note, you can also generate CO2 directly at a fire by releasing certain dry powder chemicals from other types of extinguishers. Things like sodium bicarbonate, which is just common baking soda, or potassium bicarbonate.
Baking soda puts out fires.
When heated by the fire, these chemicals decompose and release CO2 gas right where it's needed, providing a local, effective fire suppression.
Fascinating. Okay, so we've covered what fire is, what it needs, and how to put it out. But have you ever noticed that not all fires even look the same?
Definitely not.
A simple candle flame dances with light while charcoal just glows. What's going on there? Let's now dive into the equally fascinating world of the dance of the flame, exploring its different types and intricate structure.
Sounds good.
So not all burning is the same. We actually categorize combustion into different types. First up, let's talk about rapid combustion.
Okay, rapid combustion. This is probably the most common type you observe in your daily life. It's characterized by its speed and immediate noticeable effects.
Like what?
For example, when you light the gas burner on your stove in the kitchen, you turn the knob, click the lighter.
And whoosh, blue flame.
Exactly. The gas burns very quickly and immediately, producing clear heat and a distinct flame. This rapid and energetic reaction is characteristic of rapid combustion. The process is quick, often accompanied by visible light and a clear release of thermal energy.
Okay, makes sense. Gas stove equals rapid combustion. Then there's a more dramatic and often dangerous type called spontaneous combustion. This one sounds a bit scary, and for good reason.
It definitely can be. Spontaneous combustion occurs when a material suddenly bursts into flames without any external spark, flame, or obvious direct cause being applied.
It just lights itself.
Essentially, yes, it seems to ignite on its own. A classic chemical example is phosphorus, which we mentioned, with matches certain types burn spontaneously in air at room temperature because their ignition temperature is incredibly low.
Okay, but does this happen with everyday stuff?
It can. In real-life scenarios, this phenomenon is responsible for a variety of hazards. For instance, Spontaneous combustion of coal dust has caused numerous disastrous coal mine fires around the world. It ignites underground seemingly out of nowhere due to trapped heat building up from slow oxidation combined with oxygen.
Wow, in mines. Scary.
Very. Another common example, maybe closer to home for some, is the spontaneous combustion of hay bales in agriculture if they're baled too damp. Or oily rags left in a pile like in a garage.
Oily rags, really?
Yes. In these cases, slow oxidation reactions, sometimes helped by microbes in the hay, generate heat. If this heat can't escape easily, like in the middle of a big pile, it builds up until the material reaches its own ignition temperature.
And then poof.
And then, poof, a sudden unexpected fire. It's why ventilation and proper storage are so important. And while we're talking about unexpected fires, think about forest fires. While some are indeed caused by natural things like lightning strikes or extreme heat during long, dry summers, sadly, most forest fires, as shown in Figure 4.4, are often due to human carelessness. Things like unextinguished campfires, discarded cigarettes.
Ah, yeah. That's preventable.
Totally preventable. Understanding spontaneous combustion is critical for fire prevention, especially in industrial or agricultural settings, or even just being careful with potentially hazardous materials at home.
Good points. And finally, for maximum impact, the most impressive and often destructive type of combustion. An explosion.
Yeah.
It's definitely the one that grabs your attention.
An explosion is essentially a very, very rapid form of combustion. It occurs suddenly and generates a huge amount of heat, light, and a significant amount of sound.
The sound is key, right? Or bang.
Absolutely. All accompanied by a large volume of gas being liberated very, very quickly. Think of a firecracker.
Yeah. Bang. Flash. Smoke.
Exactly. Or the combustion of gunpowder in a confined space, like in fireworks or historical cannons. It's an extremely rapid, often confined form of combustion that unleashes a tremendous amount of energy in a very short burst.
A burst of energy.
Yes, leading to pressure waves that create the sound and the destructive force. The key distinctions here compared to other types of combustion are the extreme speed of the reaction, the accompanying loud sound, and that rapid, forceful liberation of gases.
Got it. Rapid, spontaneous explosion. Different types. Now, we've talked a lot about types of burning, but have you ever really looked closely at a flame itself?
Like really observed it.
Yeah. Have you wondered why some things burn with a bright, flickering flame, like our friend the candle, and others just glow steadily, like charcoal? Let's take a candle for a moment. Look at Figure 4.9. What is it about that candle that makes a flame dance so vibrantly?
Okay, the key to forming a flame, that visible dancing thing, is vaporization.
Vaporization, like turning into a gas.
Exactly. Only substances that vaporize during burning produce a flame. Let's break down the candle example because it illustrates it perfectly. The solid wax in a candle doesn't actually burn directly.
It doesn't.
No. Instead, when you light the wick, the heat from the initial flame first causes the solid wax near the wick to melt.
Okay, it melts. Liquid wax.
Then, this molten wax is drawn up the wick through something called capillary action, much like water climbing up a thin paper towel.
Okay, wax climbs the wick.
As it gets closer to the flame's heat traveling up the wick, the molten wax gets hot enough to vaporize. It turns into gaseous wax vapors.
Ah, wax gas.
Pretty much. It is these wax vapors that then mix with oxygen from the surrounding air and actually burn to form the visible luminous flame we see.
So the flame you see is actually burning wax vapor, not the solid wax or the liquid wax.
Correct. The flame is the zone where the wax vapor is undergoing combustion.
That makes so much sense now. So, following that logic, why doesn't charcoal, which we know burns and gives off heat and light, why doesn't it produce a visible flame? Why does it just glow?
Precisely because it doesn't vaporize significantly under normal burning conditions.
It stays solid.
Largely, yes. Charcoal is primarily composed of carbon. When it combusts, the solid carbon reacts directly with oxygen right there at its surface, producing carbon dioxide and releasing heat and light. But it mostly remains in a solid state. It doesn't form significant amounts of gaseous vapors that would then ignite to create that dancing flame structure.
So it's burning, releasing energy, but no vapor, no flame.
Right. It's undergoing combustion and releasing energy, often glowing brightly because it's hot, but without that intermediate step of vaporization that creates the visible dancing flame. This distinction between direct solid-phase combustion and combustion of vapors helps us understand the visual differences we observe in various burning processes.
Fascinating. And we can actually see the unburnt bits inside a flame, can't we? pretty cool when you demonstrate this in class. It's like peeking inside the flame's chemical factory.
Yes, you certainly can. It's a wonderful demonstration of incomplete combustion happening right within the flame.
How do we do that again?
If you carefully hold a clean glass plate, or maybe a microscope slide, and introduce it into the luminous part of a candle flame, that's the yellow, brightest part, as illustrated in figure 4.11.
So, stick glass in the yellow part.
And hold it there for about 10 seconds or so, you'll observe something quite striking when you pull it out. A circular blackish ring will form on the glass.
Black stuff. What is it?
This black ring is actually soot. And soot is made of tiny, unburnt carbon particles.
Unburnt carbon.
Yeah.
Inside the flame.
Yes. This phenomenon provides tangible proof that combustion isn't always perfectly efficient, especially in that specific part of the flame where the oxygen supply might be limited. The carbon atoms from the wax vapor don't have quite enough oxygen readily available right there to fully react and turn into carbon dioxide.
So they just stay as carbon.
They remain as solid carbon particles for a moment, glowing yellow because they're very hot, before eventually either burning up higher in the flame or escaping as soot. It shows the process isn't perfect.
That's why a flame isn't just one uniform blaze of light and heat then. It's actually highly structured, with distinct zones, kind of like layers within an onion, right?
Exactly like layers. Each zone has its own characteristics and, importantly, its own temperature. If you take a close look at figure 4.13 in your textbook, it illustrates the detailed structure of a candle flame. It's truly intricate.
Okay, walk us through the layers. What's at the very center?
Okay, at the very center of the flame, closest to the wick, you have the innermost zone. This zone typically appears dark or almost black.
Dark. Why?
It consists primarily of unburnt wax vapors that haven't yet mixed with enough oxygen to ignite, or perhaps they've just started to vaporize from the wick. Because there's very little active combustion happening right there, it's actually the least hot part of the entire flame.
Least hot at the center. Interesting. Okay, moving outwards.
Moving outwards from the dark center, we find the middle zone. This is the part that's typically bright yellow and visibly luminous. This is where you see that characteristic candle glow.
The bright part.
Right. In this zone, partial combustion occurs. This means there's enough oxygen mixing in for some reaction, but not quite enough for complete combustion. This leads to the presence of those glowing, unburnt carbon particles, the soot we just talked about. They get heated up and glow yellow. The zone is moderately hot.
Okay, yellow, moderately hot, partial combustion, soot. Got it. What's next?
And then there's the outermost zone. This part surrounds the yellow zone. It's usually a pale blue color, and it's often barely visible, especially if the room is bright.
Blue. Like a gas stove flame.
Exactly like that blue. The blue color indicates that complete combustion is taking place here. Why? Because this zone has the most access to the fresh oxygen from the surrounding air.
Makes sense, it's on the outside.
And crucially, because of this complete and efficient burning with plenty of oxygen, the outermost zone is also the hottest part of the entire flame.
Hottest on the outside. Not the bright yellow middle.
Correct. The blue, almost invisible outer layer is where the temperature is highest.
Wow. Okay, that's maybe counterintuitive. And this hottest outermost part of the flame is super important for some very skilled professions, like goldsmiths, right? They really leverage this scientific understanding in their delicate work.
Exactly. Goldsmiths, as beautifully illustrated in figure 4.44, are a perfect example of how practical application meets scientific principle. They often use a metallic blowpipe.
A blowpipe? What for?
They use it to blow air gently, which directs the flame, specifically aiming the outermost, hottest zone of the flame onto the gold and silver they are working with.
Why the outermost zone?
Because these precious metals have very high melting points. By directing the most intensely hot part of the flame where complete combustion occurs and temperatures are highest, they can efficiently and precisely melt the gold and silver to shape them or join pieces together.
So they know exactly which part of the flame to use.
Absolutely. They are directly leveraging the science of flame zones to perform their intricate, high-temperature work efficiently. It's a wonderful, real-world application of what we're learning right now.
It really is. Well, brilliant. Let's transition now into our final, but perhaps most impactful section. Fueling our world, what makes a good fuel and its impact.
Okay, the bigger picture.
We've talked a lot about fuels throughout this deep dive, what they are, how they burn. But let's simplify the definition again, just to be clear. Fuels are essentially sources of heat energy.
Energy sources.
We use them for practically everything, right? From cooking our food at home to powering massive industries that produce everything we use, and of course, getting us from one place to another in cars, trains, planes.
Absolutely essential to modern life. And as we touched upon earlier, they really do come in all three states of matter.
Remind us again?
We have solid fuels, like the wood and coal that have powered civilizations for centuries. Then there are liquid fuels, such as petrol, kerosene, and diesel, which are vital for transportation and many types of engines. And finally, gaseous fuels like LPG and natural gas, widely used for domestic cooking and heating, and also in some industrial processes.
Solid, liquid, gas.
When you look at the wide variety available to us today, maybe like in Table 4.3 in your textbook, you can truly appreciate how each type of fuel plays a specific and crucial role in different applications. They're tailored to different energy needs and different ways of using that energy.
So, okay, imagine this. You're an inventor, a brilliant scientist just starting out, maybe one of you listening right now. And you were tasked with designing the perfect, the most ideal fuel imaginable. What would it be like? What properties would it absolutely have to possess to be considered ideal?
The elusive ideal fuel. It truly would be a marvel of engineering and chemistry, wouldn't it?
Totally.
An ideal fuel would, first and foremost, probably need to be incredibly cheap.
Cheap, yeah. Accessible.
And readily available to everyone everywhere. That's important too. It would need to burn easily, but at a moderate controlled rate, not so fast that it's dangerous or explosive unless you want it to be, but not so slow that it's inefficient for heating things up.
Controlled burning.
Crucially, it would produce an enormous amount of heat for its mass or volume. You'd want maximum energy output. High efficiency.
Get the most energy out.
And perhaps most importantly in today's world, it would leave behind absolutely no undesirable substances or pollutants when it burns. Zero emissions, no harmful byproducts, zero environmental impact.
Wow. Zero impact. That's the dream.
And finally, ideally, it would also be easy and safe to transport and store without needing super complex or expensive infrastructure. That's a truly tall order, isn't it? Covers a lot of ground.
It sounds like something out of science fiction. So with all those criteria, what does this all mean for us in the real world? Is there actually such a thing as an ideal fuel out there right now powering our homes and industries?
Sadly, no. Not yet, anyway. The reality is that no single fuel currently available perfectly fits every single one of those ideal criteria. Not even close for most of them.
No perfect fuel.
No. We always have to make trade-offs when choosing a fuel for a particular application. We select the fuel that best meets our specific needs for that particular use, carefully balancing factors like its cost, its availability, its efficiency, how much energy it actually produces, and increasingly, its environmental impact.
So it's always balance.
It's about finding the best fit for the job, given the current options, rather than chasing an absolute perfect one that doesn't yet exist. This constant search and optimization for better, cleaner, more efficient fuels is a huge area of scientific research and engineering right now.
That makes perfect sense. So if we're always making trade-offs and balancing things, how do scientists actually compare fuels scientifically, like quantitatively? Is burning 1 kilogram of wood the same as burning 1 kilogram of LPG? Intuitively, we know LPG gives off way more heat, but how do scientists measure this difference precisely?
This raises an important question that directly addresses fuel efficiency and allows for that comparison. To compare fuels scientifically and quantitatively, we use a standard measure called calorific value.
Calorific value.
It has a precise definition. It's the total amount of heat energy produced when exactly 1 kilogram of a fuel undergoes complete combustion.
1 kilo completely burned. How much heat comes out?
Exactly. The calorific value is expressed in a specific scientific unit, the kilojoule per kilogram, written as kJ/G. It's a standardized way to measure the energy content packed into different fuels, allowing for direct comparison of their heating power on a weight basis.
So in simple terms, a higher calorific value means more bang for your buck, right? Or more heat energy for every kilogram of fuel you burn. That's a really clear way to compare them.
Precisely. More energy density. For example, if you look at Table 4.4 in your textbook, you'll see some fascinating comparisons. Hydrogen gas, for instance, has an incredibly high calorific value, around 150,000 kilograms. It packs a huge punch.
150,000, wow.
In stark contrast, something like cow dung cake, which is used as fuel in many parts of the world, is much lower. It typically ranges from only 6,000 to 8,000 kilograms.
Big difference.
Huge difference. This significant difference in calorific values helps us understand why we choose certain fuels for specific applications where high energy output is critical, like using hydrogen compounds and rocket fuel, versus fuels used for simpler, less energy-intensive purposes like basic cooking fires. It's all about getting the most useful energy out of what you're burning efficiently.
Okay, that's super useful. Now, while fuels power our lives and enable so much of our modern world, their increasing consumption, as we all know, has some very serious downsides.
The consequences.
Burning fuels creates harmful byproducts that directly affect our environment and our health. It's often referred to as the dark side of this incredible energy source, and it's something every grade A scientist absolutely needs to understand. We can't ignore it.
You're absolutely right. We have to look at the whole picture. Let's break down some of these main harmful byproducts. First, many common carbon-based fuels like wood, coal, and petroleum products, when they burn, especially if the burning isn't perfectly efficient, release unburnt carbon particles into the atmosphere.
The soot we talked about earlier.
Exactly, soot, but also other fine particulate matter. These are tiny microscopic particles. They are dangerous air pollutants.
Why are they dangerous?
When inhaled, these microscopic particles can penetrate deep into our lungs. Because they're so small, they bypass our natural defenses. This can cause or worsen serious respiratory diseases, things like asthma, bronchitis, and other chronic lung conditions. They make it difficult for people to breathe and significantly impact overall public health, especially in cities or areas with lots of traffic or industry.
Okay, so particles are bad for breathing. What else?
Then there's a truly insidious gas that can be deadly, often without any warning signs. It's a silent killer that we hear warnings about, especially during winter months with indoor heating.
Which gas is that?
That's carbon monoxide, chemical formula CO. This very poisonous gas is produced when fuels undergo incomplete combustion, remember that. It means there isn't enough oxygen available for the fuel to burn completely to carbon dioxide, CO2.
Incomplete combustion leads to carbon monoxide.
Correct. Carbon monoxide is particularly dangerous because it is odorless, colorless, and tasteless. You can't detect it with your senses at all.
Invisible danger.
Exactly. When inhaled, it gets into your bloodstream and binds to the hemoglobin in your red blood cells much more readily, much more strongly than oxygen does. It essentially kicks oxygen out.
So your blood carries CO instead of O2.
Yes, effectively. This prevents oxygen from reaching your vital organs and tissues, including your brain. It's why we're always strongly advised, for instance, never to sleep in a room with a burning or even smoldering coal fire, or use barbecue grills indoors, especially in unventilated spaces.
Because the CO builds up.
Carbon monoxide can silently accumulate to lethal levels, leading to carbon monoxide poisoning. This can cause headaches, dizziness, nausea, unconsciousness, and tragically even death while individuals are sleeping. It's an invisible but potent threat.
Truly scary. Okay, let's connect this now to the bigger picture that we hear so much about in the news, something that impacts our entire planet. Global warming. How does the burning of fuels contribute to this massive environmental challenge that affects everyone, everywhere?
This is a critical global issue, absolutely. Most fuels, especially the fossil fuels like coal, oil, and natural gas that power so much of our world, release carbon dioxide into the atmosphere as a primary byproduct when they undergo complete combustion.
CO2, we breathe it out, plants use it. Why is more of it a problem?
Well, CO2 is what's known as a greenhouse gas. In the atmosphere, it acts a bit like the glass panels of a greenhouse. It lets sunlight in, but it traps some of the heat that radiates back from the Earth's surface, preventing it from escaping into space.
Like a greenhouse effect.
Right. Some greenhouse effect is natural and necessary to keep the planet warm enough for life. But an increased concentration of CO2 in our atmosphere, resulting mainly from the massive burning of fossil fuels since the Industrial Revolution, traps more heat.
So the planet warms up overall.
This enhanced greenhouse effect is widely believed by the vast majority of climate scientists to be the primary cause of global warming, the gradual long-term rise in Earth's average atmospheric temperature.
And what are the consequences of that warming?
This rise has cascading and potentially devastating effects across the planet. It leads to the melting of polar glaciers and ice caps.
Which raises sea levels.
Exactly, which in turn causes sea levels to rise globally. This threatens low-lying coastal regions and islands with increased flooding, erosion, and potentially displacing millions of people. It also contributes to more frequent and intense extreme weather events like heat waves, droughts, heavy rainfall, and disrupts ecosystems and agriculture worldwide. It's a huge, complex problem.
Wow, okay. And it's not just CO2 causing problems from burning fuel, right? We also get something called acid rain, don't we? Which can cause widespread damage to our crops, our forests, and even historical buildings. How does that happen?
Yes, acid rain is another significant environmental consequence linked to fuel combustion. Burning certain fossil fuels, particularly coal and diesel fuel, releases sulfur dioxide, SO2, into the atmosphere. Sulfur is an impurity in these fuels.
Sulfur dioxide.
Additionally, the high temperatures inside petrol engines in cars cause nitrogen and oxygen from the air to react, releasing gaseous oxides of nitrogen.
Nitrogen oxides, too.
When these gaseous oxides, the sulfur dioxide and the nitrogen oxides, get into the atmosphere, they react with water, oxygen, and other chemicals up there. They dissolve in rainwater as it falls through the atmosphere, and they form weak solutions of sulfuric acid and nitric acid. This creates what we know as acid rain.
Rain that's actually acidic.
Yes, more acidic than normal rain. This altered, more acidic rainwater is extremely harmful to our environment when it falls back to Earth. It can directly damage the leaves of our crops and forests, making trees more vulnerable to disease and pests. It can acidify lakes and rivers, harming fish and other aquatic life.
What about buildings?
It slowly corrodes and damages historical buildings and monuments, especially those made of marble or limestone, dissolving them over time. And it also changes the chemical composition of the soil we rely on for agriculture, leaching out important nutrients and potentially releasing toxic metals. It has widespread effects.
Yeah, so, okay, after hearing about all these really serious effects, the air pollution, the carbon monoxide poisoning risk, the huge issue of global warming, acid rain damaging everything, what does this all mean for the future of our planet? You grade 8 scientists listening, are we just stuck with these harmful effects from burning fuels as we continue to power our world? Is there any hope for cleaner energy solutions?
That's the crucial question, isn't it? And it raises an incredibly important and ultimately hopeful point. Thankfully, the answer is a resounding no. We are definitely not stuck. This is where human ingenuity, science, and engineering come into play.
Okay, good. What's happening?
Cleaner alternatives are actively being researched, developed, and importantly adopted on a larger scale all the time. For instance, one example mentioned in your chapter is compressed natural gas, CNG.
CNG, right. We mentioned that earlier as a fuel.
Yes. It's increasingly replacing diesel and petrol as a fuel for automobiles, buses, taxis, even some cars in many cities around the world.
Why is CNG considered cleaner?
The reason is simple and impactful. When CNG burns, it produces significantly fewer harmful products compared to petrol or diesel. It releases much less carbon monoxide, fewer unburnt carbon particles, less soot, and negligible amounts of sulfur dioxide because natural gas is mostly methane with fewer impurities.
So fewer pollutants overall.
Significantly fewer. It's a tangible, positive step towards a cleaner future for transportation and helps mitigate some of the serious air quality and environmental impacts we've just discussed. And of course, beyond CNG, the bigger shift happening is towards renewable energy sources like solar power, wind power, geothermal, hydropower.
Right, generating electricity without burning anything.
Exactly. These represent an even cleaner future, aiming to eventually replace fossil fuels for many applications, especially electricity generation. The transition takes time and effort, but the solutions are being developed and deployed.
Wow, what an incredible journey we've taken today through the whole world of combustion and flame. It's been quite the deep dive.
It really has.
We started by defining what burning actually means on a chemical level, that reaction with oxygen.
Releasing heat and light.
Then we uncovered the 3 essential conditions fire needs to exist.
Right.
Fuel, air, and heat. The fire triangle.
Can't have fire without all 3.
We learned how we strategically control fires by removing one of those elements, using things like water or CO2.
And why water isn't always the right choice.
Very important point. We explored the different types of combustion, rapid, spontaneous, and explosion.
From a gas stove to a firecracker.
And finally, we delved into the fascinating layered structure of a flame itself, those different zones.
The dark, the yellow, and the hot blue outer part.
We've covered so much ground.
And we certainly didn't stop there. We also explored what makes a good fuel, or rather, the quest for an ideal fuel.
Right, the trade-offs.
How we scientifically measure its efficiency using calorific value.
kJ per kilo.
And crucially, we faced the very real and significant environmental impacts of burning fuels.
Yeah, the downsides. From respiratory issues caused by unburnt carbon, to the silent threat of carbon monoxide, and those huge global challenges of global warming and acid rain.
It's truly a vast, vital, and incredibly interconnected topic. Combustion really does affect almost every aspect of our lives and our planet.
So you, our curious grade 8 learners at School on X, you now have, I hope, a deep understanding of combustion and flame that truly goes far beyond just memorizing definitions from your textbook.
We hope so.
From the simple, everyday act of lighting a birthday candle to understanding complex global climate issues and thinking about the future of energy, these fundamental scientific principles are absolutely essential to making sense of the world around us. This knowledge isn't just for tests, it's truly for life.
So true. So thinking about those pressing global challenges of climate change and the ongoing urgent search for cleaner, more efficient, and more sustainable fuels, here's a final thought to ponder for all of you listening.
Ooh, a challenge.
If you, with all your newfound scientific understanding, could invent a truly ideal fuel, one that embodies all those perfect properties we discussed earlier, cheap, available, efficient, clean, easy to handle, what unique qualities would it possess? What would it be made of? And maybe more importantly, what do you think would be the single biggest, most formidable challenge you'd face in making that dream fuel a reality for everyone on Earth?
That's a great question to mull over. What is the biggest hurdle? We encourage all of you to take this new lens of combustion and flame and start observing the world around you with fresh eyes.
Yeah, look closer.
Maybe next time you see a flame, whether it's on a gas stove or a campfire or even just a match, you'll think about its different zones and how they work. Or perhaps you'll start noticing the sources of fuels used in your own community, the petrol station, the power plant, the delivery trucks, and consider their impact on our environment and our collective future.
Science is everywhere once you start looking for it. Keep that curiosity burning bright. It's how we learn and how we grow.
Absolutely. Well, thank you so much for joining Grace and me, Adam, for another deep dive into science here from School on X.
It's been great exploring flames with you.
We can't wait for you to continue your learning journey with us next time.
Bye for now. Bye, everyone.